very welcome to this webinar. So my name is Sebastian Schlecht. I have the honor to chair this session today. I'm myself an associate professor for signal processing at the FAU in Erlangen, Germany. And I have the pleasure to welcome Archontis Politis today, our speaker. Also from kind of the subfield of audio processing, and to say a few words about him. So Archontis is now an assistant professor at Tampere University in Finland. Before that, he did his master degree at the ISVR, the Institute of Sound and Vibrations in Southampton, and after that, a doctoral degree at Aalto Acoustic Labs, so also in Finland. That's also kind of why we know each other, because I also had the pleasure to spend a few years at this lab after Archontis time, but he was still around because he then moved not too far then to Tampere University, where he is working now. And so he's been working for many, many years in parametric spatial audio and has contributed much through software packages and also writing or contributing to a book on this topic. And my understanding is that since he moved to Tampere, he combined this with sound event localization, sound event detection, and really, I think, bringing in these different kind of techniques, and this will be also kind of today's content of the talk. And I think that's a really nice, timely combination with lots of potential for applications. So that's as introducing words. So floor is yours.
Thank you, Sebastian, for the introduction. It saves me also from the effort of going through this bio. It's just to add here that in the past, big part of my research were very much on spatial audio capture and rendering. And after I moved to Tampere, as you mentioned, there has been here, it's a group mostly of audio analysis, and big part of the work here was essentially bringing that kind of spatial audio tools to audio analysis. Very briefly about my part in the group here in audio research group of Tampere University. That has been a research group with also a long tradition in music information retrieval in the past, sound source separation, and I would say the last 10 plus years, very strong contributions in machine listening and context-aware audio analysis. And after I joined this group, my role was kind of the spatial audio guy, the guy who handles more than one microphone, since typically many of these tasks were not considering, let's say, multi-channel or processing or spatial audio information. They didn't have to necessarily, and they didn't do. So the presentation is very much on that space of, let's say, machine listening and acoustic scene analysis. And if we talk about this umbrella term from the aspect of traditional machine learning audio, essentially it's kind of the framework that tries to develop computational models that can recognize sounds of relevance in audio streams and recordings, and then also extract some useful information about either the sources themselves or the activity or the states of the sources, or what kind of agents or objects generated these sound events, interactions of the sources, or some kind of overall information about the scene or the state of the scene that has these sound events. Typically, this overall machine listening is split and studied under certain more specialized tasks, either depending on the information granularity that we want to extract or the application itself. Some very common tasks are audio tagging, try to find like what kind of sounds are present in a recording, or sound event detection, which is trying to classify the activities, try to classify the sounds of interest in a recording, but also find when they are active in the recording, so temporal and semantic tracking of the sounds of interest. Then acoustic scene classification, just labeling recordings based on what kind of scene it is, like a urban square or a train station. Then we have action recognition by acoustic monitoring, anomalous sound detection for, let's say, industrial monitoring applications, or urban monitoring, and many, many others like that. These applications are becoming, I would say, more and more ubiquitous, even at the consumer level. And just to bring an example, everybody that has an Android device, for example, can download this live transcribe and sound notifications app by Google, which you can select what kind of sounds you want your device to be listening. And then if it detects one of those, then it sends you some kind of notification. For example, for a door knock or a smoke and fire alarm, tea kettle. Yeah, a good example of sound event detection at large scale. And one more note on this general machine listening, a very strong, let's say, center of gravity for that community, I think, from 2013, when this started, it was this DK's challenge and the respective workshop, where this small community at the beginning organized it, and then gradually it attracted more attention and it grew through the years. At least from 2016 till today, it has been constantly growing, and it has been introducing more and more advanced tasks. In the beginning, it was just acoustic scene classification, sound event detection, and tagging. And now you have tasks like unsupervised anomalous sound detection for industrial monitoring, sound event localization and detection, text-driven audio question answering and retrieval, and many other tasks. Right. Okay. Now getting to our more specific topic, I would still call what we're trying to do machine listening, but with a spatial dimension. So spatial machine listening or spatial acoustic scene analysis, it's not really a common term. I just made it up, but it's just to bring focus on the fact that here we aim to, apart from all the semantic temporal like information extraction from the recordings, we also want to extract spatial information from the audio streams. In the most basic setup, that can be just source directions or positions. At a higher level, we can be trying to extract trajectories of those sources or from the agents or objects that produce certain sound events. We can also be trying to infer actions in space and interactions. And we can also try to infer some scene properties from the sound events themselves, spatial scene properties from the sound events themselves. For example, some kind of arrangement of the sound scene, obstacles that moving sound sources are avoiding, or boundaries, for example. The applications for that task are, as you can imagine, can be quite wide, because it gives, let's say, a quite complete description of the sound scene, both at a temporal, semantic, and spatial level. So we can have like urban, domestic, industrial monitoring when we are interested also where sound events of interest are happening, human-machine interaction, augmented and selective hearing, robot audition, spatial context-driven audio processing, and also scene summarization and captioning with a spatial dimension, and many, many others. In its most basic implementation, at least we could think of, kind of a model or a method that tries to provide some information like that would be simply a model that at least it can recognize and localize relevant sounds in an acoustic scene over time. And by relevant sounds, we typically mean that we define some set of sound classes of interest, and then the model has to focus on these specific ones as the most relevant ones to our application. So that brings us to this sound event localization and detection task that we have worked on for some time, and also others. At the first level, it can be seen as a combination of two very well-established audio processing problems. One is the source localization kind of task, which is one of the most classic tasks, very heavily studied with signal processing methods and traditionally developed by the signal processing array processing community, which, however, in its kind of typical setting, it only tries to infer dominant source positions in the sound scene without caring about the source type or the source signals themselves. On another side, we combine with the other side of the task is sound event detection, one of the most classical tasks of this machine learning audio community, which, however, traditionally it has been done only with monophonic input, no spatial information used, even though there are some works that they show some benefit using multiple channels to do this kind of accurate temporal tracking of the target classes of interest. So the sound event localization and detection can be seen as a combination of these two tasks at the same time. It has some distinct properties also that the combination brings. So, for example, compared to sound event detection, we typically require a higher temporal resolution because the localization requirements, especially if we are interested at moving sources, they require a finer temporal granularity in our estimates than typical sound event detection, which may be estimating things in a few seconds or even longer. A lower temporal resolution. Also, because you are bringing spatial information, we have the capability to resolve multiple instances of the same class, which is something that traditional sound event detection setting does not do. If you have, it doesn't matter for the output of the system if you have one dog barking at the same time or two dogs barking at the same time at different positions. However, the celled model should be able to resolve such a scenario. On the other hand, compared to sound source localization, a model trained on these target sounds that we want to focus will ignore other localized sound sources in the scene, whether it's noise or not noise, but out of target interference, which is something that classical sound source localization methods don't care in a way about doing. They're not set for that. Also, one can say that in multi-source scenarios, we typically have less association problems between the estimates and the true sources compared to traditional sound source localization, because the model distinguishes these different classes of sound. So, of course, if we can do that for many classes, then most likely we have just a few instances per class that we want to localize, and these are well then disassociated, while in the sound source localization case, all the sources are grouped together, and that creates this additional problem of complex data association between estimates and sources. Okay, yeah. Now, trying to think a little bit how to set up such a model, it can be done in various ways. One way is kind of intuitive and simple way to take one sound event detection model and some sound source localization model or method and just do late fusion on the outputs. Also, one can use sound event detection model. Typically, these are machine learning or deep learning models, and still combine with some traditional signal processing localization method, or use also a trainable, like data-based model for sound source localization. On another hand, one can try to model the whole problem jointly. So a single model that tries to achieve both localization and detection, and that can also be done in different ways. In one way, such a model can still have a separate output that does this sound event detection and a separate output that does this source localization. And then you optimize both components independently. So that can be seen as a kind of a multitask setup from a machine learning point of view. Or if you do have a suitable representation that represents both localization and detection at the output, then you optimize for that directly. And that would be kind of a single task setup of the problem. Then there are other possibilities with respect to how you represent the problem, especially in terms of localization. Are you try to set it up as a regression-based direction of arrival or location estimation, estimating continuous vectors, for example, for the positions of the sources, or whether you set it up as a classification-based direction or position estimation, where you classify activity in spatial sectors on your like region of potential locations. Okay, to give a more specific example, this is an early model that we published in late 2018, which we called CellNet back then, which is a very, very simple model in a way, especially considering today's like advanced models, where we have the multi-channel audio. We take the channels and we perform a short-time Fourier transform. We get the spectrograms, and then we pass this multi-channel magnitude and phase spectrograms into a stack of convolutional neural network layers. And these are followed also by two recurrent layers that after the feature extraction of the CNN layers, they perform a kind of temporal, they track kind of the temporal dependencies across the features. And then we split the inference into two heads. One is doing the sound event detection, giving probability per class about the temporal activity for each class. And at the same time, we have as many vector outputs, giving the direction of arrival also per class for the respective localization. Such a model could track only a single instance per class because of how it was set up. By design, we decided to use kind of very generic input features, just multi-channel magnitude phase spectrograms, so that it can easily be used to different spatial formats or arrays. And we saw that it can have a decent performance in a variety of input formats. At least we were testing first order ambisonics and like a circular microphone array in the original paper. Right. One other important thing for training such a model, since this is a fairly complicated task, is of course data. Like we need a lot of data, we need a lot of diversity, and the options that people use at the moment is either virtual acoustic simulations, where we simulate spaces and source receiver impulse responses, and then we spatialize sound events, that's of course kind of the first choice for most people use that a lot, and we can generate very diverse conditions in that way. Another option that is a bit more real acoustically is to capture room impulse responses in real spaces and then use those to spatialize sounds. Of course, then your set of conditions that you capture depends on the number of impulse responses that you capture and the number of rooms. And then we have another option, which is the most difficult one, which is to actually record real spatial sound scenes and annotate the activity of the sound events of interest in these sound scenes, plus the spatial positions of those sounds when they are active. For our efforts in the beginning, we used simulations, of course, quite heavily, but we also wanted to bring this a bit more this real acoustic aspect. So we captured a lot of impulse responses in about 15 different rooms here in Tampere University, where we were moving a loudspeaker slowly in trajectories inside the room, and then from this, like a loudspeaker playing some broadband noise excitation, and then from these recordings, we were extracting the room impulse responses at every 1 degree resolution approximately, as seen from the array. And we collect about 250 such source trajectories, resulting in about 65,000 room impulse responses. And we could also use, because these were kind of very densely extracted, we could also use this afterwards in synthesis to kind of emulate moving sources for various simulation scenarios. However, after some point in the development of the methods, we decided that this simulation way with virtual acoustics or room responses is not enough to give us an idea how things will be performing in real conditions. So we did actually the work of trying to collect a data set of real sound scenes, where then we also we combined a 360-degree camera, 32-channel spherical microphone array, from which we extracted different formats like ambisonics and tetrahedral microphone array for the data sets that we worked with. And we also had a motion capture system to track the main sources of interest and wireless microphones for close recordings to the sources. And using all those things together and human annotators also for the sound events, then we managed to get about 11 hours of such sound scenes in about 16 different rooms for 13 target sound classes of interest. And these were captured here in Tampere University in one part, and also in Tokyo in some spaces by Sony as a collaborative effort. I can give a short example how this dataset looks if we overlay the labels, let's say, on the recordings. Oh, no.
Okay, sure. Then let's start.
Okay, I'll jump to a few more.
दो चार महीना बाद आओ आवा तरी बस ऐसा नहीं
Sorry.
let's try it
Well, oh, I think is this is my favorite song.
is
I-
really
I'm not even kidding.
wow
This, can you please pass it to me? I
Yes.
want to hear it.
Yeah.
in the
yeah
Just feel it
Yes.
against your ears.
Yes, please.
It's a great. Oh.
Wow, thank you.
Yeah, no problem.
See you again.
Yeah. Have a good day.
Yeah, same to you.
Okay, I hope you get the idea. Yeah, and finally, one other thing we had to consider was how to evaluate the performance of these models. And eventually, what we went for was to adapt kind of classic classification and detection metrics as used, for example, in sound event detection, but adapted to include spatial information. So, for example, measuring F-scores in or error rates for every sound event, sound class and sound event of interest, but considering, for example, true positives only when that predicted object was close to the reference. Otherwise, it would be considered as a false positive. And essentially, using these spatial thresholds, we could adapt the effect of localization performance to the classification performance. And this can be tuned to suitable thresholds based on the application of interest. Right. So one important thing to mention is that the development of that sound event localization detection task, also from our side, was very strongly connected to this decades challenge, because after the initial publication in late 18, we were quite excited about it, and we did a proposal for a new task in this decades challenge, which was accepted. And after that, it has remained as a task every year. So now it's 7 years total. And I think, apart from the fact that this decades challenge is very, very well organized, and it has a very, very nice interface and the schedule on time to get the results, publish them. People can very easily find information there. It generally has the benefits of a challenge that we provide a standardized development set of multi-channel recordings and spatial annotations. We have a standardized evaluation set that we keep the labels and we evaluate the submissions. We also provide a baseline that gives kind of a point of reference for comparison, and we use common evaluation metrics. So people can really test their methods against the baseline and between each other in a kind of a standardized manner. And the task has, I would say, a small but quite active community with strong participations both from academia and industry. There have been about 115 academic affiliations and 44 industry affiliations that they have submitted in independently or in teams submissions to the task up till today. And if I want somehow to make a distinction between the different years of the challenge, how it has developed, generally it has been getting harder and harder every year. But I would say that there are two distinct phases. The first one is based on these synthetic recordings for training and evaluation, using these room impulse responses that we collected in Tampere University. While the second phase, we moved the task into evaluation of real sound scenes, where we used this STARS 22-23 dataset of real recordings that I mentioned earlier. And also there have been other developments, like from 2023, we also allowed the use of video input. And also last year, we had a bit different setup that instead of 360 audio and video, we switched to kind of a stereo format and normal planar video to test the task in a kind of more normal media related, let's say, scenarios. All right. So moving a little bit to more specific developments. I'm not going into great detail because there is. I decided it was maybe more useful to cover wider ground than like focusing on more specific technical details. Yeah, I hope, however, you can, whoever is interested, you can reach me, and also so there is lots of information to find in this Decades Challenge results from every year. But going through the development of SELD, at least through the Decades Challenge, in the beginning, we saw more submissions that they were trying to fuse sound event detection models with traditional signal processing or like parametric localization methods, which I think is generally a very reasonable, very good idea, especially a good, efficient option for low resource and edge devices and real-time processing. However, doing these things independently, I have to say that association of the localization estimates and the sound event detection output is not straightforward. So one has to invest some intelligence handling this, fusing these two things on top, or decide to take a hit, let's say, on the performance of the system. So in terms of the challenge, in the first one in 2019, there were 3 submissions doing that. Then in 2020, there was 1 submission. And after that, essentially everybody had moved only to DNN-based, deep learning-based models for detection and localization. Then another development was this distinction between classification-based SELD or regression-based SELD. In the regression, we have to decide on a fixed number of vector outputs that we try to track. So that can be either 1 per class or even more per class. With a classification way, I would say one has more flexibility to handle multi-source scenarios. However, if we are moving, let's say, to full sphere localization and we want a good spatial resolution, then one has to handle hundreds or thousands of classes, which becomes a challenge in itself to train effectively, let's say, in multi-source scenarios. Our baselines from the beginning were using a regression-based approach. And also with respect to the challenge, the first couple of years, there were more proposals using a classification-based approach, but then later, most methods moved to regression. Especially also because we were doing this kind of full sphere localization and we had dynamic sound scenes with lots of moving sources. There have been also later kind of more advanced classification-based SELD proposals, for example, the SAD YOLO by Kim et al. And probably others. Another development was, let's say, moving away from these generic magnitude phase spectrograms that we proposed, at least in the beginning. Already from the first challenge, people spotted that probably using more refined spatial features would prove more effective for the task. And that's absolutely true. So already in 2019, CAO was proposing to extract intensity vectors from the ambisonic signals, which is a very strong narrowband spatial feature, and add that to the inputs to the network, and also generalized cross-correlation sequences for the microphone array format, which is another kind of very classic spatial feature. And then later, Nguyen and her team, they proposed these salsa features and these salsa light features, which are also kind of inspired very strongly by classic sound source localization features, like it's essentially the first is principal Engel vectors of the spatial covariance matrix of the microphone signals, and the second is a much faster version, which is kind of normalized intermicrophone phase differences. And also those were proved very effective. And the decay's baselines we were contributing essentially after these features were appearing, were integrated into the baseline in the following years. Another nice development was this kind of multitask or single task celled modeling and representation. In the beginning, all the systems were having this separate inference heads, one doing the sound event classification, the other doing the localization. It's kind of a clear distinction how to represent your output and how to form your training losses and then to combine them. However, there was this idea that some kind of joint celled output representation will may have some benefits, provide stronger coupling between the sound event detection and the source localization, and you don't need any loss balancing. So one such solution was proposed by Shimada in the team from Sony in the case 2020, where they introduced this activity coupled direction of arrival. Essentially, it combines the sound event detection with the vector representation of the direction of arrival estimation, where the vector points to the direction, but the class activity is encoded into the magnitude of the vector. If it's close to 0, the class is inactive. If it's close to 1, the class is most likely active. So ACDOA proved to be quite popular, and it was adopted also by the DK's base line, and it's probably the most popular representation now in the challenges. Then another development was this capability of celled models like multi-source localization to detect simultaneous instances from the same class at different locations. As I mentioned briefly, that was not really treated in the original baseline, neither in the first submissions, in the first and the second challenge, more or less, even though there were such cases in the simulated recordings we were providing. So the first proposal, I think, that was trying to solve that was proposed by Kao in 2020 and 2021, where they kind of reformulated the problem as instead of predicting detection and localization per class, instead having a fixed number of output tracks that can have any class, and they would be determined essentially by the maximum polyphony that we expect in the sound scene. If we expect to have a maximum, let's say, 5 simultaneous sounds of interest at any given time. There you still have kind of association problems to solve like in traditional multi-source localization. So these were trained with permutation invariant training techniques. And then a little bit later, also Shimada kind of extended the ACDOA vector representation to this multi-ACDOA representation, which is essentially just a straightforward extension of instead of using one vector per class, we use now 2 or 3 vectors per class to manage to detect these multiple instances. This needs a little bit of special techniques to train effectively, but if one does that, then it's equally effective, let's say, to the track-wise approach. And both of them are used by various teams submitting models today, and the DK's baseline has followed with this multi-ACDOA representation. Another development what's also interesting was spatial data augmentation. Data augmentation is extremely prominent in, let's say, audio machine learning tasks, but spatial data augmentation was something that I would say developed mainly along this celled task. And essentially it's very valuable because, as we said, the task is fairly complicated and you may have a limited amount of data. So being able to create more versions of it with more spatial diversity definitely is going to improve your generalization performance. So early on, people, for example, exploited symmetries of the spatial formats, mirroring, for example, the sound content across principal planes and also their labels in this ambisonic format or in the tetrahedral microphone arrangement, while others used more kind of elaborate techniques like using the ground truth labels and forming beamformers to the sound events, extracting the sound events, and also or steering vectors of the array for those sound events, and then reusing these signals or components to spatialize, to kind of respatialize the sound events at new directions or use the same kind of directions to create more, more spatial combinations. Right. Another big development with the task was this introduction of this audiovisual input instead of audio only input, which happened in 2023. And generally, the DK's challenge has stayed away from video to keep it more audio focused. But in our case, the committee gave the okay because I think in the end, everybody thought that it kind of makes sense for this specific task. So it makes sense because, of course, there is very strong spatial information in video for foreground audiovisual objects. And I think also more importantly, it points to a way to manage to scale the task to real recordings out on the wild. Because as we said, collecting real recordings and annotating them is very hard. So one avenue we can foresee to go around this problem is to use video information for kind of self-supervision if you have both video and audio. So a simple example of how that can be done. This is the DK's audiovisual baseline that essentially the left branch is the main audio branch, where the first part is pretty much the same cellnet as when we started. Then there are some more modern components like self-attention for better temporal modeling. But then on the right, we take the video frames, we pass them through a competent pre-trained computer vision network like ResNet 50. Then we process these extracted visual features in some suitable way to manage to fuse them with the audio related features. The fusion is done also in a learnable way, a trainable way with cross-model attention. And then the fused features essentially contribute to the estimation of the sound event detection and localization similarly as before. So that task was introduced in parallel with the audio only task. So we had two tracks, one audio only and one audio visual. We were expecting to see a very big boost on the audiovisual track compared to the audio only. It didn't happen. So essentially, the audiovisual track proved to be harder than it sounded. In the first challenge, only one team did better on the audiovisual than the using only audio, marginally. In 2024, we had small gains by 3 teams on audiovisual input compared to audio only. So gradually, people seem to be refining their audiovisual models. But I would say that there is still plenty of room for improvement. Then one more development was that in 2024 we introduced source distance estimation, which is so essentially extending from only direction of arrival estimation to full 3D positional localization for the sound sources. Source distance is a rich also spatial information. One can do different kinds of processing depending on the proximity of a source. We know that it was going to be hard because with a small array, we know that the spatial cues associated with the source distance are quite weak as you move away from the array very quickly. So similarly, the results from the submissions were showing that the task was hard, but we had decent performance for the top performance of the challenge. And that was about 20 to 25% mean relative error, which 20% mean relative error means that if the ground truth distance was 1 meter, then you had 20 centimeters of error. If it was 10 meters, then you had 2 meters of error. Yeah, we also saw some interesting choices by the participants. For example, some submissions just ignore distance estimation to not take a very large hit in the ranking because they could do then much better direction of arrival estimation. Then some systems that they were estimating the distance, they were actually performing worse than just guessing the mean distance of the training set. So yeah, there is still definitely plenty of room for improvement. And there was also some interesting development of distance-related input features passed to the model, additionally to the previous ones, like direct to diffuse ratios or depth maps, if somebody was using the video too. Finally, one interesting development I want to mention that has happened outside of the DK's challenge till now at least is this text-grounded sound event localization detection and spatial audio understanding or reasoning in general, where people train models together with text input, trying to predict essentially the correct information using natural language, which can be very useful in human-machine interaction. In our case, we try to query spatial properties about the sound scene with natural language questions, and models like that typically combine some spatial audio encoders together with text encoders, or using like full LLMs integrated in some part. And the output itself can be also an answer in natural language, all like normal model outputs. So we had a publication like last year where we were using a celled model together with questions that they were asking, for example, whether a source is present in the sound scene, or if the model can list all sound events in the clip, or if it can list stationary or moving sound sources, or if it can find the leftmost, rightmost, topmost sound source, and also sorting questions like if the model can sort events by azimuth or elevation or distance, or temporal questions like sort events by order of appearance. Yeah, there are many papers I think appearing in that domain recently, and I think there will be many more. So to close the presentation very quickly, I will go through some what I believe can be future developments and open problems related to sound event localization and detection. One is self-supervision. We need to solve that problem, as I said, in order to move to real recordings at scale that we don't have labels, spatial labels for. And I believe the audiovisual route there is the most promising. There are already some early proposals towards that direction, still lots of space for work there. The next is large-scale pre-trained celled models. In terms of sound event detection, pre-trained models have been very successful now. They have been fine-tuned and used in many different specialized applications. However, in the case of celled, pre-training in such a general way, I would say it's very difficult because of the dependence to specific microphone array formats for the localization aspect. This problem is difficult. It's an open problem also just for sound source localization, like learning-based sound source localization. There have been some early proposals towards that direction, but they don't really solve the problem. They go kind of around it. So also still lots of space for work there. Then one can imagine more general and or hierarchical celled models where we don't just detect these directions for these specific classes, but they are more open and flexible. They can detect sound events both for localized or ambient diffuse sound classes without location information, or it can do sound source localization at the same time for out of target class localized sounds, and then it can do celled for the rest. So such a model can cover many more real cases in a way. Then we can go beyond this point direction of arrival representations, because in reality we have extended sources, large objects producing sound. So to do that, we have to move towards kind of redefinition of the output representation. Maybe it's something like spatial segmentations or more like acoustic imaging, for example. Then I haven't seen much work on, let's say, tracking agents instead of sound sources across multiple sound events. So for example, instead of speaker tracking across space, track a human through the different sound events that they produce or their actions and interactions. Also, there is still lots of space for improvement on better realistic scene simulations. Both on the acoustic side, we can already do a lot of things there, but still, for example, simulating multi-room environments with dynamic source and receiver scenarios, including real device capture information. We can do it in a way, but it takes a lot of work. It's not straightforward for most. So lots of space for still development there. And more importantly, we also need some kind of realistic temporal sound event synthesizers that they produce sequences of sound events that correspond to real actions and interactions in a sound scene. Because at the moment we're just randomizing stuff. And finally, of course, we always need more real spatial annotated data for evaluation. Especially they can be application specific, and that would be extremely valuable for people working in that field. And I think that concludes the talk. Thank you. Thank you very much for listening.
Hey, Archontis, thank you very much. That was very nice. Great overview on many of your activities, but also the activities of the community. Yeah, so we have some time for questions. I just mentioned it again, right? So for the webinar is kind of recorded up to now, but the discussion part will be then not recorded anymore. Yeah, are there any questions?